Harrison is the Director of Research at the Space Technology and Science Initiative at Arizona State University. She has a PhD in geology with a specialization in planetary science and exploration from the University of Western Ontario, and is an expert on the geology of Mars, commercial academic space partnerships, and mission operations. She was a member of the operations team for instruments on the Mars Reconnaissance Orbiter and the Curiosity rover, and is a science team collaborator on the Opportunity rover and on the Mars 2020 sample caching rover, which is scheduled to be launched next June. She's a contributor at the Planetary Society and has been active in public outreach through organizations such as the Girl Scouts, NorWestCon, the Mars Society, and the National Space Society. Most importantly, she identifies herself as a professional Martian, and Fox News identified her as the director of Mars. We're very, very fortunate to have her here on this team. Please welcome Dr. Tanya Harrison.
Wake this up, it should start working again. So I think that bio just describes that I just never sleep and I really like Mars, so hopefully I can convey one of those things to you tonight. I want to preface this by saying all of the pictures that you're going to see in this talk tonight are actual photographs of Mars, and a lot of them you've probably never seen before because they tend to come from data sets that are not very commonly processed just because they're really difficult to work with. So I'm assuming most people in this room have seen The Martian. Show of hands? Okay, kind of figured that would be the case. So I think when people think about weather on Mars in the general public, they tend to think of stuff like this. And while The Martian is a really scientifically accurate movie in a lot of respects, this dust storm that sets off the whole thing is nothing like what we actually have on Mars. So we're going to kind of go through some of the weather patterns that we see on Mars. A lot of pretty pictures. This is basically a talk to show off pretty pictures. That's a good reaction. So just to give you some basics about Mars, it does have an atmosphere. Some people don't know that. It's predominantly carbon dioxide with a little trace amounts of nitrogen, argon, oxygen, carbon monoxide, and 210 parts per million of water vapor, which doesn't sound like a lot, but it is enough to influence weather, and we'll actually focus a lot on stuff related to water in the atmosphere in sort of the second half of the talk. The surface temperatures have a huge range depending on where you are on the planet, so the poles versus the equator, and if it's summer versus winter. So right now you're probably seeing lots of news stories that say it's warmer on Mars than it is in Canada or the Midwest right now. It's a little bit of a miscomparison because right now those weather data are coming from the Curiosity rover, which is at the equator in kind of late summer on Mars. So it's the balmiest time of year on Mars compared to the coldest time of winter on the Earth. But right now, if you're at the poles, it's more like -200 degrees, and that's kind of more representative of what we have for most of Mars, most of the rest of the year. So a lot of the major drivers of weather here on Earth are the same things that control the weather patterns on Mars. Seasons, so where you're getting heating versus cooling. Temperature gradients between different areas, which come from elevation changes or land cover changes. So on the Earth, those land cover changes tend to be the difference between, say, oceans and land, or vegetated areas and not vegetated areas. On Mars, it tends to be the difference between places that are covered with ice versus no ice, or differences in albedo, which is basically just a measure of the reflectance of the stuff you're looking at, so the dark areas versus the light areas. We also have differences in air pressure gradients, and then just the Coriolis effect from the fact that the planet rotates just like the Earth does. Mars is tilted about the same amount toward the sun as Earth is. So Earth is about 23.5 degrees, and Mars is 25 right now. But it actually swings wildly. On Earth, we wobble a little bit, like a couple of degrees over the course of about 60,000 years. And over that same time scale, Mars goes from about 0 to 60. So it's wobbling like this. And it makes crazy changes in the climate and where the ice is on the surface, but we're seeing it in kind of this weird interglacial period right now. It also has a really highly elliptical orbit, so at some points in the year, it is really close to the sun, corresponding with over here. So northern winter, southern summer, Mars is really close to the sun. But in southern winter, northern summer, it's really far away from the sun. So there's more dramatic differences in summer versus winter in each hemisphere. And the seasons are about twice as long as they are on Earth because the year on Mars is about twice as long. So it's 667 Martian days, which is about 686 Earth days. And a term that you'll hear me say a lot throughout this talk is L sub S, which is colloquial for solar longitude. And it's basically a measure of where Mars is around the sun in terms of a 360-degree ellipse. And it's the way that we measure time on Mars when we're trying to figure out what season it is on any given day for the rovers or the satellites that we have in orbit. But why do we actually care about monitoring the weather on another planet? There are a lot of really important reasons for us to look at weather on Mars. The biggest one is keeping the rovers safe, which is very relevant right now with everything that's happened with Opportunity. We use it for picking future landing sites, so we want to make sure that we don't go to a place that is really prone to storms throughout a lot of the year because that's not really good for the health of your rovers. We use it for planning orbital imaging because we have a very limited amount of bandwidth between Earth and Mars, and so we don't want to waste time taking pictures of places that are cloudy unless we're actually trying to image the clouds for some reason. So we try to plan around the weather patterns so that we get the best data that we can at any point in the year. We're also trying to monitor climate change. The south polar cap of Mars is disappearing and we're not quite sure why. We discovered this by accident about 20 years ago now, so we monitor that over the course of multiple years. And we monitor changes on the surface, so changes in the distribution of dust and ice and things like that over the course of multiple seasons and multiple years. Skip that one. So we do a lot of stuff with monitoring Martian weather now, but we've actually been monitoring the weather on Mars since the 1600s. So these are some sketches from Huygens in 1659, where you can see some of the different albedo patterns, those differences between the dark areas and the light areas, through a really simple backyard telescope. And Huygens was able to make out Syrtis Major, which is one of the main albedo patterns on Mars, and the south polar cap. So since a lot of you guys use telescopes, you're probably used to seeing south as up. So this here is actually the south polar cap on Mars through this telescopic view. Moving forward into the 18th century, the astronomer Maraldi noticed changes in the south polar cap over time, again with a very basic telescope. When Mars is really close, you can actually see these changes. It's really incredible. And then in 1784, Herschel suggested for the first time that these caps were made of ice and noted the presence of an atmosphere on Mars. So it's pretty early on that we knew there was stuff happening with weather and the polar caps. We move farther ahead into the 1800s. We started to see observations of things that astronomers thought could be dust clouds based on what color they were. And in the 20s, when we started getting the ability to do spectroscopy, people were actually able to detect things like oxygen and water in the Martian atmosphere. The astronomer Adams was able to determine from the concentrations of these things that Mars was probably an extreme desert environment. So the idea that Mars was this lush place with these canals and Martians that Lowell was putting forward in sort of the science fiction literature was never really widely accepted by the scientific community. So even though it was a really great idea for us to think that we had all these awesome Martians, nobody really thought this was the case because we had this type of data pretty early on. Again, most people here have probably looked at Mars through a telescope, but if you haven't, this is just an example of what Mars looks like through a 10-inch telescope. So you can make out a lot of surface features when it's relatively close. So this here is Syrtis Major, that part that Huygens was able to see through his telescope in the 1600s. And then we've got the south polar cap here. So those are some of the main areas that you can pick out with these telescopes. But now we have satellites on Mars, so we can get even better weather data. And the first camera that we really had dedicated toward looking at the weather on Mars was on Mars Global Surveyor. It was called the Mars Orbiter Camera, or MOC. And this camera operated around Mars from September of 1997 through November of 2006. And it gave us about 4.5 continuous Mars years of weather monitoring. So with this camera, we got a global color image of Mars almost every single day in that time period at 250 meter per pixel resolution, which is really incredible. We don't even have that great of a data set that's publicly available for the Earth in a lot of cases. And so we were able to use this to look at what the weather does on Mars. These are just some examples from a single day from this particular camera. Unfortunately, with the way Mars Global Surveyor orbited, there were gaps over the poles during certain parts because we just couldn't slew the spacecraft quite enough to fill in all those gaps. But you can make out a lot of really interesting features through this view. So this is the northern polar cap here. This is a hole over the southern polar cap. All these wispy things here are clouds. More clouds, more clouds, lots of frost down here. So we can monitor a lot of the changes in weather every single day with this particular camera. Or we could when Mars Global Surveyor was still operating. In March of 2006, the Mars Reconnaissance Orbiter got to Mars, so it overlapped with Mars Global Surveyor for a little bit of 2006. We were hoping there might be a little bit more overlap. Unfortunately, we lost Mars Global Surveyor kind of unexpectedly. But we were able to replace the mock monitoring with a camera called the Mars Color Imager, or MARSI. And for scale, this is someone's hand with a Q-tip. This is actually a camera that you can hold in your hand. And for anybody that's following the Juno mission at Jupiter, the camera that's on there is basically kind of a modified version of this particular camera. So it's just more radiation hardened, so it's a lot heavier, but kind of the same size. And this particular camera takes interesting pictures. It takes a single strip from pole to pole as it orbits from the South Pole toward the North Pole, going around the planet in what we call an ascending orbit. And then we mosaic those strips together to make a global view of the planet. So that's why we have some of these little blurry areas here, because it's a 180-degree fisheye lens, and so it's not very sharp when you're at the edges of it. So when you mosaic all those strips together, it kind of looks like this. But it still gives us a nice global view of Mars, again, almost every single day of the mission at 1 kilometer per pixel resolution for people that number means anything to. And we can map project these images to actually give us this nice round view of what you would see with the Mars Global Surveyor camera instead there. So we're gonna go through some of the different types of weather patterns that we see on Mars. Probably the most famous one are dust storms. Again, especially with what's happened to Opportunity recently. This is an example of a rather large dust storm that happened near the Spirit rover back in 2008, also known as MER-A. And what we would do with this is from the MARSI camera, anytime that we would see a storm heading toward the rovers, we would keep an eye on it, and if it got within about 1,000 kilometers, we would say, hey, you guys on the rover team, like, watch out, this is kind of heading your direction. And if it got within 400 or 500 kilometers, then it was kind of danger mode, batten down the hatches, close all your dust covers, don't plan to do anything that's really power intensive because you don't want to drain the batteries if you're not getting enough sun to the solar panels to keep the batteries charged up. Obviously, when your storm is this large, you can't drive the rover out of the way, so you just kind of hunker down and hope that you make it through it. So this one, between November 6th and November 7th, it got much closer to Spirit in the course of that day. This one ended up going over the rover. Luckily, it survived this particular storm, but this was one of the ones that we were most worried about in Spirit's particular case. This next slide used to be about the 2001 dust storm until we got the 2018 dust storm. So you probably all heard in the news, in May of last year, we got the strongest dust storm that we've ever seen in the entire time that we've been observing Mars. Not just with satellites, but with telescopes. So from like the 1920s onward, we have never seen anything this strong. Hopefully this video will play. There we go. So this is a view from MARSI of what Mars looked like on May 28th of last year compared to July 1st. You can't really see any of the surface because the atmosphere is so dusty. And this dust storm lasted for months. This is pretty common. So during southern summer, what tends to happen is that sunlight warms the dust particles on the surface of Mars, and it causes them to lift higher into the atmosphere than they normally would, and it creates this wind cycle. And that wind kicks up more dust, so it creates this huge positive feedback loop where it's just self-reinforcing. And at some point, it gets so much dust into the atmosphere that it ends up circulating around the entire planet and then blocks the surface from view. So we call these global dust storms kind of colloquially, but it's a bit of a misnomer because the storm itself is not global. In this particular particular case, the storm got to be about 3/4 of the size of the planet, which is almost global. It's larger than anything by far that we've ever seen on the Earth. But it just gets big enough that it lofts enough dust into the atmosphere that it can circulate around, and that's when it looks like it's a global storm. And they don't happen every year on Mars, but when they do happen, they always happen at the same time of year. So we know when to look out for them, and we can watch for certain signals to see if we might get one or not. This one was unusual because it happened very early in what is usually dust storm season, and it was so strong, and it lasted for a really long time. So this one really caught us by surprise, and it's helping us learn a lot more about how these dust storms might function on Mars. This is another animation just showing the red area is the dust storm kind of highlighted between May 31st and June 11th, which is the day that we lost contact with Opportunity. With the locations of Opportunity and Curiosity marked on this map. So you can see the storm started out as a very small local storm, just kind of north of where Opportunity is when this starts over. So it starts up here, really quickly engulfs where Opportunity is. Unfortunately, the strongest part just kind of hung out over Opportunity for a very long time, and then it ended up spreading out over most of the rest of the planet. So this animation that was released by NASA doesn't even encompass the storm until the point of its strongest point. It just goes up to the point where we lost contact with Opportunity. So one thing that we do with Opportunity, or did with Opportunity on a regular basis, is that we take pictures of the sun. It's so depressing to put everything in the past tense now. So I worked on the PanCam, the panchromatic cameras on Opportunity, which are the color eyes of the rover. I worked as a payload downlink, which basically means I downloaded the pictures from the rover and then looked at them from the standpoint of a geologist to make sure, is there anything cool in this image that we should be studying? And from the standpoint of an engineer, is the camera functioning properly? And I was on shift the week that we lost contact with Opportunity. This was what the sun looked like to PanCam on the Wednesday of that week. And we take pictures of the sun to see how much dust is in the atmosphere. It gives us a value called tau, which is a dimensionless number that tells us basically how much crud is in the air. On Friday, it looked like this. And I got a bunch of frantic emails from people on the team that said, is there something wrong with the camera? Is the dust cover closed? Are we not pointed at the sun? Is something going wrong? And I had to send the horrible email that said, no, the camera's working fine, we just can't see the sun. And this is pretty much the last image that we ever got back from the rover. The storm was so strong that at the beginning, this is what it should look like on a normal day at high noon to Opportunity. And over the course of a few days, it got to the point where the sun was completely blocked out. These are simulated views based on estimating the tau values. So tau of 0 would mean the atmosphere is like nice and perfectly clear. The strongest storm before this one, I think we had reached something like a tau of 6-ish. This storm was a tau of 10.8. It might have been as high as 11.2. There's a little bit of controversy there because we don't actually have a great measurement on the ground since we lost contact with the rover. But at the point that the dust storm was at its strongest, it would have been as dark for Opportunity at noon in the middle of the day on Mars as it would be on a moonless night in a rural area here on the Earth. That's how much dust was in the air. Wow. We can keep an eye out for these global dust storms by looking for things called cross-equatorial storms. So this is a topographic map of Mars where the blue areas are the lower elevation and then the yellow and red and white go into the higher elevation. Opportunity was kind of about here. Curiosity is over in this area. And we can keep an eye out for global storms because they tend to be storms that cross the equator. And they go across two areas of low elevation. We have this Acidalia storm track. So you'll see here there's this low elevation kind of basin here. And then the Utopia storm track, which again kind of goes from the northern hemisphere down into the southern hemisphere. And these basically act as giant topographic funnels if the storms are big enough to kind of push them down toward the equator. These usually happen in late spring and summer for the southern hemisphere. And like I said, they're funneled by these topographic controls. And usually when we get these storms, they'll spiral off the edge of the polar cap. This black line here, it's kind of thin, but it's the equator if you can see it from where you are. Usually the storms will hit the equator, and by the time they get that far, they fizzle out just because of the way the circulation cells in the atmosphere work. If any of you are familiar with Hadley cells here on the Earth, We have the same kind of circulation cells on Mars, so you don't tend to see storm systems cross the equator very often on Earth because of these types of patterns. On Mars, sometimes they do, and that's usually the danger sign that this could become a very large storm. Sometimes those storms can make it all the way to the southern polar cap. We had sort of a global storm back in 2007, also called a planet encircling dust event. That's the less exciting name for these things. This is an animation of images from the Marcy camera. So we very quickly ended up with another situation where you couldn't really see much of the surface. You can see the tops of the large volcanoes over here. This is Olympus Mons, and these are the Tharsis volcanoes. That's Valles Marineris there. You can basically only see the large volcanoes because they're so tall, they kind of poke out the top of the atmosphere. This particular storm took months to subside before we get to a point where we could really image the surface again from orbit. But the interesting thing about this one is, if we start the video over again, if you pay attention to Acidalia up here, the storm comes down and smashes into the edge of the south polar cap there and then kind of explodes. And that's usually the danger sign. Once it hits the edge of the southern polar cap, there's such a huge temperature gradient there between the ground that is covered with ice versus the ground that is not, that it causes these huge wind patterns and it just lofts a ton of dust into the air. And the interesting thing is, sometimes you get these huge storms, and when they dissipate, the surface looks exactly the same as it did before the storm hit, and we don't understand how that works because you've put so much dust into the air. But other times we see some big changes. So this here again is Syrtis Major, that area that Huygens could see, before one of our global dust storms and after. So you can see there's been a lot of dust deposited here. On Mars, typically the darker bluer areas are the less dusty places, and then the lighter redder areas are the more dusty places since the dust is very red. There's also here, this arrow is pointing to some changes on the surface, and then this one here, so we have like this area that was dark is no longer dark anymore. These tend to come off of things called polar spiral storms. And this is one of my favorite weather images that we got back from Mars from the Marcy camera. These form due to temperature and pressure gradients where you have the ice-covered polar cap next to the non-icy ground right next to it. So we get these huge spiral storms that come off the edge of the polar cap. And they're spiral shaped because of the Coriolis effect, so just because of the fact that the planet is rotating. And they're really common in spring and summer on Mars because that's when you have the biggest temperature difference between the warm ground and the icy ice. And these things can be absolutely massive. So in this example, this here is one of those spiral storms, and this is the northern polar cap. So the storm is basically the size of the entire polar cap. And they can kind of spiral off and go down these storm tracks and end up going all the way down to the south polar cap, where at this time of year it's winter, so the cap is really, really far north, so it doesn't take much for the storm to go all the way down, hit the edge of that cap, and then explode. And we see storms like this on Earth,